We're going to start with Chapter R, and we're going to cover 3 sections out of this review chapter to get started. So this chapter is a review of functions, graphs, and models. All right, so we're going to start with section R2 on functions and models. So the things we're going to go over here, hopefully you've seen all these before, but we're going to review what you need to know about them in order to proceed further in this course. So the objectives here are to be able to determine whether or not a correspondence is a function, just basic function definition, find function values using graphs and equations, graph functions and determine whether or not the graph is that of a function, and graph functions that are piecewise defined. All right, so our definition of a function. A function is a correspondence between a first set that we call the domain and a second set, which is called the range, such that each member of the domain corresponds to exactly one member of the range. That is the key phrase, exactly one. So everything in the domain must be used, and it can only be assigned to one member of the range. All right, example 1. Determine whether or not each correspondence is a function. So this first one is an example using Microsoft stock. So we have the domain, the date March 14th, 2006, assigned to the range in which the stock value was $27.23. Second element, a date corresponding to a dollar amount, another date corresponding to a dollar amount. All right, so this relationship shown in this mapping is a function because each member of the domain, the dates, corresponds to one member of the range. So that meets the definition. So you would say, yes, this would be a function. All right, part B is the relationship of squaring a number. So the domain and the range here are given by a set of numbers in the domain. The function is identified as squaring, so the operation that's happening to create the range is you're squaring this number. So 3 squared is 9, 4 squared is 16, 5 squared 25, and negative 5 squared is also 25. This also is a function because each member of the domain corresponds to only one member of the range, even though you have 2 separate members of the domain corresponding to the same value. The definition says each of these numbers goes to exactly one number, which it does. Okay, so these numbers can get used twice over here, but what can't happen is you can't have a number from the domain having 2 arrows come off of it. So that is also a function. All right. Third example for part C is baseball teams. So domain, Arizona, Chicago, and Baltimore. Range, Diamondbacks, Cubs, White Sox, and Orioles. So we have a city and then the baseball team over here. So Arizona pairs with 1 baseball team. However, Chicago has 2, Cubs and White Sox, and Baltimore is 1. So this would not be a function because we have a member of the domain, Chicago, that corresponds to 2 separate elements over here in our range, Cubs and White Sox. So that would violate the definition. These elements can only go one place. We have one of those that goes 2 places. So that's not a function. All right, if we switch them around and use the teams as the domain and the cities as the range, it would look like this. So this is similar to the example that we saw earlier with the squaring example. So this should be a function, right? Each member of the domain goes to exactly one place, even though Chicago has 2 teams. So this is a function because each member of the domain corresponds to only one member of the range, even though 2 members of the domain correspond to Chicago, right? Each of these only has 1 arrow, so that is yes. All right, so moving on here to using equations for functions to find function values. All right, so we have an example here, the squaring function f given by the equation f of x equals x squared. They want us to find f of -3, f of 1, f of k, f of the square root of k, f of 1 plus t, and f of x plus h. All right, so hopefully from before you remember how this works. F of a number x is found by taking the x and squaring it. So if I want to find f of -3, that means -3 replaces the x. So we take -3 and square, we get 9. F of 1 means take 1 and square it, which is still 1. F of k is k squared. That's all we can do because we don't have a value for k. F of the square root of k, again, the square root of k is our input. We're going to square it, so when you square the square root, you just get k. F of an expression, 1 plus t, means that expression, 1 plus t, is what's getting squared, and this is just foiling this out, 1 plus t squared. If you wrote it out and did FOIL, right, the first two, the outer, the inner, and the last, and combined your like terms, you would get 1 plus 2t plus t squared. And then f of x plus h is similar. X plus h gets squared. So x times x is x squared. X times h is xh. That's the outer and the inner. So you get 2 copies of of xh. And then plus the h times h is h squared. So again, if you don't know the shortcut to squaring a binomial, which is square the first term, multiply these two things together and double for the middle. So that's the xh doubled. That's the 2xh. And then square the end. You would just write out x plus h times x plus h, do the distributing, and combine like terms. All right, a function f is given this time by f of x equals 3x plus 5. This is another example similar to the last one. Find f of 4, f of -5, f of 0, f of a, and f of x plus h. So ideally here you should try this on your own. Pause the video, try it on your own, see what you get, and then turn it back on to see and check and see if you did this correctly. All right, so f of 4. Plug 4 in place of x into your function definition. So f of x is 3 multiplied by x plus 5. So 3 times 4 plus 5 is 12 plus 5 or 17. F of -5. 3 times -5 plus 5. Again, you're plugging -5 in for x. -15 plus 5, -10. F of 0, plug 0 in for x. That's 3 times 0 plus 5. 0 plus 5 is 5. F of a means 3 times a plus 5, or 3a plus 5. And then f of a plus h, again, the a plus h is getting plugged into the function in place of x. So 3 times the a plus h plus 5. This time it's just distributing 3, so 3a plus 3h plus 5, and then that's all you can do with that. And that's it. All right, this time our function is given as x minus f of x equals x minus x squared. A function subtracts the square of an input from the input. They're just describing in words what this says. All right, this time we're going to find f of 4. F of x plus h, and then this expression is f of x plus h, which you'll already have from doing this. From that, subtract f of x, which is given, and then divide everything by h. This formula is known as what we call the difference quotient, and it has very important applications in calculus, okay, that we will get to very soon. Okay, but it's just here as practice on evaluating it. All right, so f of 4. So our function here, x minus x squared. So 4 minus 4 squared. If I plug in 4 for the x's, that's 4 minus 16, or -12. F of x plus h. So this would mean our input is x plus h minus x plus h squared. So this x plus h is the x minus, and then again, that's the x squared. So this is x minus x squared, but this is replacing x. Okay, so now we've got, I'm just squaring this, so x plus h minus, keep the parentheses here, we're just squaring the x plus h, so again, x squared plus 2xh plus h squared. If You get that from foiling. Here we're then going to distribute our negative sign, so minus x squared minus 2xh minus h squared if you bring the negative sign through the parentheses. Right? So that is the answer for f of x plus h, right? We got this. The next part wanted you to find f of x plus h minus f of x divided by h. So we just did f of x plus h and got all of this. So this x plus h minus x squared minus 2xh minus h squared, that's the f of x plus h part. Then we're told to subtract f of x, so that's the subtract, and then this was f of x that we were given initially. Make sure that's in parentheses because the distributing will have to happen in the next step. And then the h was given on the bottom. Next step is to distribute the negative sign. So we're going to distribute the negative sign through the parentheses right here. Minus x, that turns this to plus x squared. Then we're going to clean up the numerator. So notice the x's cancel out, the x squares cancel out, and you'd be left with just the h minus 2xh minus h squared. So what they've shown here is with those terms being the only ones left, because this term is gone, as are the last two, they factored the h out of what's left, leaving 1 minus 2x minus h. And then this h was still on the bottom. And then when this h is factored out, these h's cancel, leaving 1 minus 2x minus h. And the stipulation here is that h cannot equal 0 because it's in the denominator. You can't have a 0 in your denominator. Okay, so here there is a step here that I probably would not have skipped, that you would have h minus 2xh minus h squared, right? Then the h would have factored out from there. All right, so this one you should try on your own. So I would pause the video. Our function here is f of x equals 2x minus x squared. We're going to pretty much do the same thing here. This should be minus f of x plus h minus f of x over h. So f of 4. 2 times 4 minus 4 squared. 8 minus 16, negative 8. F of x plus h. 2 times x plus h minus x plus h squared, just the x's are getting replaced with x plus h. So distributing the 2x plus 2h. Remember this would have been FOILed, x squared plus 2xh plus h squared, but then the negative would distribute through there and changing all these to minus signs. So that would be the result of f of x plus h. So then your f of x plus h result, which was all of this, so that's these first 5 terms here, minus f of x. Notice they've already removed the parentheses here. So minus f of x, if you're subtracting this whole thing, you're going to get minus 2x, and then your subtracting will distribute here and give you plus x squared. So your 2x's cancel out. Your x squares cancel out, so you're left with 2x minus 2xh minus h squared when they cancel. That's the step that they didn't show in the last example. Divided by the h. Then the h would get factored out, leaving 2 minus 2x minus h in the parentheses. Then the h's can cancel, so you get 2 minus 2x minus h. This is something you will have to know how to do later on when we get into the calculus chapters. This is one of the main, involved in one of the main definitions. Okay, so this, being able to simplify it and get through the algebra is important. All right, moving on here to graphs of functions. The graph of a function is a drawing that represents all of the input and output pairs. So all the values of the domain paired up with each corresponding value of the range as an ordered pair. If you plot all of those points and connect the dots, that's what a graph would be. So when the function is given by the equation, the graph of the function is the equation y equals f of x. So it shows a pattern. All right, so here we're going to ask to graph f of x equals x squared minus 1. So depending on what you remember from previous courses, some functions you might have seen frequently and they're very common, so you might just know what the shape looks like. But in general, to graph a function, especially if you don't know what it's going to look like ahead of time, we just make a little table. So you have a table for the input values, plug them into your function to get the output values, and each of those then correspond to an ordered pair. So here they've just chosen an x. They chose any x because there's no restrictions on what you can choose here. So choose any x value. So -2, -1, 0, 1, and 2 is what they started with. Compute y, meaning plug those x's in and get a corresponding f of x value. So when they plug -2 into here, -2 squared, that's 4 minus 1 is where the 3 came from. -1 squared is 1 minus 1 is 0. 0 squared minus 1, -1. 1 squared is 1, minus 1 is the 0. And then 2 squared again is 4 minus 1 is a 3. So this is just the ordered pair -2, 3, the ordered pair -1, 0, the ordered pair 0, -1, the ordered pair 1, 0, and then the ordered pair 2, 3. And then those get plotted on a graph. So -2, 3 is left 2, up 3, that's this point right here. -1, 0, 0, -1 down here, 1, 0, and then 2, 3. And we can see that they line up in this shape. That's called a parabola. It's a pretty basic shape function that you may be familiar with. All right, the vertical line test. Okay, how to tell whether, if you're given a graph, if it is a function or not. A graph represents a function if it is impossible to draw a vertical line that intersects the graph more than once. So in other words, every vertical line can only touch the graph one time. All right, so our next example, determine whether each of the following is the graph of a function. Okay, so we have 4 examples here. So A, anywhere I draw a vertical line on this graph, I would only touch the graph once. So it's impossible to draw a vertical line, meaning up and down, straight up and down, that touches the graph more than once. So this is yes, this is a function. B, okay, there is a place right in here where I can draw a vertical line that would touch the graph twice. So if it's possible to find a vertical line that touches the graph more than once, this is not a function. Because if you draw a vertical line, you're basically choosing an x, and if it touches the graph twice, that x would correspond to 2 different y's. In other words, 2 different range values, and that's not allowed. So B is a no. C is also a no for the same reason. If I can draw a vertical line somewhere in here that would touch the graph more than once. So if you can find any place where there's a vertical line that hits the graph more than one time, it is not a function. So B and C are both no. And then D is, again, yes. Any place you draw a vertical line, you're only going to touch it one time. Like here, one time, right? No matter where you put it, you're only going to hit the graph once. Or maybe you put it way out here and that doesn't touch it at all. That's fine too, as long as it doesn't hit it more than one time. So A is yes, B is no, C is no, and D is yes again. So our next slide is just going to explain all of that, which I've already done. So I'm just going to kind of go through that real quick here. So that's A, yes, B, no, C, no, and D, yes. All right, our next example is an application. In 2005, Sprint offered a cell phone calling plan in which a customer's monthly bill can be modeled by the graph below, which we will show right here. The amount of the bill is a function f of the number of minutes of phone use. Okay, so number of minutes down here on the bottom, and then it corresponds to the dollar amount of the bill based on how many minutes per month. Okay, this is what we would consider something that we call a piecewise function, because notice that the function graph is determined in pieces where they're not all connected to each other, right? Or they're not all coming from the exact same equation. All right, so I'm going to refer back to this slide, but I need to move on to the next one to see what questions they're asking us about it. All right, so each open dot on the graph indicates that a point at that location is not included. All right, so under this plan, if a customer uses the phone for 360 minutes, what would the bill be? And then part B, if a monthly bill is $55, for how many minutes did the customer use the phone? Okay, so here they're wanting to know, if they're given the number of minutes used, that's the x-axis, find the bill, and then vice versa on part B. If you're given what the bill is, can you find how many minutes they talked? All right, so to find the bill for 360 minutes of use, you're going to locate 360 on the horizontal axis and move directly up to the graph. When we move across the vertical axis, it's $40. Let me just go back here and show how that's done. Okay, so 360 minutes means down here on the bottom, we're 100, 200, 360, so this would be 1, 2, 3, 4, 5. So we're in here somewhere, right? You don't really have to find exactly, because if you notice here, anywhere in this section between 3 and 400, which is where we would land, somewhere in that range here, we would land on this line segment, right? So no matter where you're at, if you're between 300, more than 300, right, up to 400 minutes, right, this is where you're going to land. And if you go then across, you're going to land at $40. The other one gives you the price to be $55. So if you find your bill in dollars up here at 55, then you're going to scroll over until you meet the graph. And then right here, the $55 bill would be for any minute value. Notice this is an open circle, so not including 600, but anything larger than 600 minutes, so more than 600 minutes, up to and including, because of the closed circle, 700 minutes. Right, so if you talk more than 600, if you talk at exactly 600, you're here, right? You're at $50. But once you pass 600, you jump to $55, and then that would be included all the way up to the 700 minute mark. Go back to the explanation. All right, so here's where they explain all that. To find the number of minutes of use when a monthly bill is $55, we found 55 on the vertical axis, move horizontally. Note that many inputs correspond to that number. So if T is the number of minutes of use larger than 600, notice not including, but less than or equal to 700, right? Because it is including 700. So that range, not including the 600, but include the 700 and otherwise in between. All right, graph the function defined as follows. So here we are given what a piecewise function definition of a function would look like, and we're asked to draw the graph. So this function says g of x equals 3 if x is equal to the number 1. Otherwise, it's negative x plus 2 for any value of x not equal to 1. All right, so the function defines g of 1. So if x is 1, all right, that's where the g of 1, the y value is 3. All other values for x that are not 1, we're going to plug those into this equation to find our ordered pairs. Oops. All right, so to graph this function, we're going to basically graph this. This would be the graph of a line with a y-intercept of 2 and a slope of negative 1. But there'll be an open dot above the value of x equals 1 because we're not including the x value of 1. So to complete the graph, we plot the point at 1, 3, because we said this says if x is 1, y is 3, at that open dot. This is what it turns out to be. So again, if x equals 1, the y value is 3. So if x is 1, the y is 3, that's the closed dot. That defines this first piece. Otherwise, this should have been negative x plus 2 was what they gave us. So the line, negative x plus 2, means the slope is, that the y-intercept is 2. The slope is negative 1, so down 1 over 1 would give me this line. But I have to put a hole here at x equals 1 because we're not using the value 1. The value for 1 is defined differently. So that would be my graph. Okay, they show the table. They're plugging in any value of x chosen that's not a 1 gets plugged into the equation negative x plus 2, resulting in an ordered pair. Notice when x was 1, they didn't plug it into the equation, right? All these are plugged into the equation, but this one's not. And then those are the points that are plotted. Notice you don't just connect all of these together. You have to know that this single point is separate from the path created by the others. All right, here's another one. F of x equals 1 if x is equal to negative 2, and 2 minus x if x is not equal to negative 2. So ideally here you should pause the video and try to do this on your own and then check to see how you did. All right, so this function is defined. So f of negative 2, this is the input, negative 2, gives me the value 1. For all other x values, anything not negative 2, you're going to use the equation 2 minus x. So that we're going to graph the line 2 minus x with an open dot above the x value negative 2, because we're not using that x. And then to complete the graph, you're going to plot at x equals negative 2, you're plotting it at y equals 1. All right, so here's our table. So if I pick negative 3, we plug into the function because that's not a negative 2, and we get the value 5. So the ordered pair negative 3, 5. If we pick negative 2, the function tells us that the y value there is 1. So that's just the ordered pair negative 2, 1. That's the one that does not get plugged into the equation. 0 gets plugged into the equation. That will give me 2, so 0, 2. 1 would get plugged into the equation, so 2 minus 1 is 1, so 1, 1. And 2 would get plugged into the equation, so 2 minus 2 would be 0, so 2, 0. Right, so if we plot the points, not this one is separate, but if you plot negative 3, 5, 0, 2, 1, 1, and 2, 0, this is the line that you would get, but at negative 2, the y value is down here at 1. So they have a hole in the line and then that point plotted elsewhere. Notice this is still a function, right? Any vertical line will only touch the graph once, because if this is where the vertical line is, it's hitting this point, but not a point on the line. All right, so just to kind of summarize this section, functions are a key concept in math. We're going to talk about functions this whole semester. Almost everything we deal with is going to be a function, right? And then the essential definition or trait of a function is that to each number in the domain, there corresponds one and only one number in the range. All right, so that is the end of section R2.